Oh, sorry about that. I was confusing myself there. Good to take a break anyway. This is straight up U sub, yeah? U is negative x, so du is negative dx. I've got the limit as b goes to infinity of, I'm going to leave this, right? Now I'm going to pull that negative outside. I'm going to leave my bounds alone because I'm going to back sub since I'm taking the limit with respect to b. We could change our bounds and worry about the negative signs and things, but I'm just going to leave them. So strictly speaking, this is false what I'm writing right now, but I'm writing this with the understanding that I'm going to sub back anyway. I've got 2 to the u du. Okay. Brings me to limit as b goes to infinity of negative 1 over ln of 2 to the negative x, so 2 to the u, barred at b1. So I just back subbed for my u there in my integral. Okay, so that's the limit as b goes to infinity of negative 1 over ln 2 to the b minus negative 1 over 2 ln 2. So evaluating at 1. Well, this is a constant. So that doesn't care about b. This is going to go to infinity here as b goes to infinity. So this in the denominator means that's going to go to 0. So this will just go, and I get that it converges to 1 over 2 ln 2. Okay, now that's the integral has converged to that value. The series isn't necessarily going to converge to that value. It doesn't converge to that value. But if this converges, that means, that implies that our original series was n equal 1 to the n? 1 over 2 to the n. Over 2 to the n converting. Okay. Since the integral test criterion were met, the series and this infinite integral both have the same behavior. So if this converges, then our original series converges. If this were to diverge, blow up to infinity, then our original series would diverge. Okay. So that's the integral test in an application. Let's use that to take a look at a new kind. We've already seen geometric and telescoping. Let's look at another kind, p-series. P-series is a series of the form let's see, 1 over n to the p. Now the important difference to note versus a geometric, let me write up a geometric at the same time, series AR to the n. In a geometric series, the fraction is fixed and the power keeps changing. So this will be like a half, and then half to the first power, second power, third power, fourth power. It's the power that's changing in a geometric series. In a p-series, this p is fixed. It's the fraction that's changing. So it'd be like 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on. Yeah? Where that p is some fixed value, some fixed power. Now if p is 1, oops. If p is 1, then we've got this n equal 1 over n. That's the harmonic series. We've already said that that diverges, and we're going to use the integral test to prove that, just a second. So let's look at this guy. In the case where p is not equal to 1. Okay? So we're going to assume p is not 1. We'll have to deal with that as a separate case. Okay? So assume p isn't 1. Well, then I have 1 over n to the p. This thing is continuous. Or if I'm looking at f of x, is 1 over x to the p. Clearly, if I evaluate that at any natural number, f at n is 1 over n to the p, which clearly is base of n. So it agrees at all the natural numbers. Now my derivative, this is x to the negative p, right? So my derivative is negative p x to the negative p minus 1, right? Straight up power rule. So bring it down, subtract 1, right? That's power rule for derivatives. But that doesn't really matter. We don't really care about all that. What we care about is this, right? That means that the derivative f prime of x is less than 0. It's a negative number, so it's decreasing. And this is going to be 1 over x to any power is continuous, right? On the interval from 1 to infinity. The only discontinuity would be at 0. But 0 is not included in this interval. So clearly all of these, regardless of what p is, are continuous on the interval from 1 to infinity. So 1 over x to the p is continuous on 1 to infinity for all p. Again, the only discontinuity possible would be x equals 0. So, and that's excluded. All right, so we verified that in general, for this p series, we can apply the integral test. So we're still assuming that p is not 1. And what we're going to look at is the integral from 1 to infinity of 1 over x to the p dx. Okay? So, well, first of all, I need to fix the bad bound. Fix the bad bound. So this is the limit as b goes to infinity, the integral from 1 to b of, let's just change that, x to the negative p dx. Now, if p were 1, I'd have 1 over x, right? And that's the one time that power rule fails. Then we have ln, and we got to treat that separate. We'll do that in a second. But if p is not 1, then I can just use straight power rule, right? So I've got the limit as b goes to infinity of, I need x to the negative p add 1. This is my power rule for integration. Add 1, divide by the new power, negative p plus 1. Okay? I need to evaluate that at b and 1. So this was just power rule for integration. Add 1 to my power and divide by the new power. Okay, let's evaluate that. Limit as b goes to infinity, we have b to the, well, let's just turn that around. So it's 1 minus p over 1 minus p minus 1 to any power, so it's just 1 over 1 minus p, right? 1 to, regardless of what the negative p plus 1 is. Okay, nice. So let's see. This is finite, right? It's just some constant, so it doesn't care about what's going on with b. The only thing that cares about b is this term here. So B is going to get big and big and big and big and big. B is going to grow forever. So let's see, if 1 minus P, if 1 minus P is anything bigger than 0, right? If 1 minus P is anything bigger than 0, then that thing's just going to grow. It might be a root if it's something between 0 and 1, it might be a root, but it's still going to grow forever. If it's something like 2 or something bigger, right, that's just going to be a polynomial function, right? It's going to grow to infinity regardless. Okay, so if 1 minus P is greater than 0, that will diverge. So let's see, 1 is less than P. So it looks like if P is less than 1, that diverges. P less than 1 implies the series diverges. Okay? Now, if on the other hand 1 minus P is less than 0, well, this B is going to drop down into the denominator. As it grows to infinity in the denominator, it's going to drive this thing to 0, and we're going to converge to this value. So if P, on the reverse side, if 1 minus P is less than 0, right, it's going to drop that downstairs and it'll converge. So in that case, if 1 is less than P or P is greater than 1, that implies that it converges. Okay. So we know that if P is less than 1, our P series diverges. If it's greater than 1, then it converges. Now, we had to worry about the fact that P wasn't 1 in 2 different places when we were doing this integration using the power rule, because it would have failed, and also here because we would have had to divide by 0, 1 minus P. Okay, so there were 2 reasons why we had to eliminate the P equals 1 case. Now let's assume that P does equal 1. Okay, so assume P does equal 1. Then we still have the same case. Integral test is going to apply, but we have the series n equal 1 of 1 over n. This is the harmonic series. This is our key example, right? The limit of those terms is 0, but let's see. So we've got this series, and we're looking at the integral of 1 to infinity of 1 over x dx. First of all, we're going to fix that bad bound. So we've got the limit as b goes to infinity, the integral from 1 to b of 1 over x dx. Now that integral I can do, limit b goes to infinity, it's ln absolute value of x barred at b and 1. So this was our one exception to the power rule, right? We had to treat it differently. It's ln. So we've got the limit, the limit as b goes to infinity of ln absolute value of b minus ln absolute value of 1. But ln of 1 is just 0. So it's the limit as b goes to infinity of ln absolute value of b. Well, as b goes off to infinity, ln goes off to infinity. So this thing diverges. It is infinity. That implies, by our integral test, that the series, the harmonic series, has the same behavior. So there's our proof. Therefore, the harmonic series diverges. All right? And now we have it in general. Our geometric series converges for absolute value of r strictly less than 1. And our p series, 1 over n to the p, converges for p strictly greater than 1. If it's equal to 1, we've got the harmonic series that diverges, and anything less, it's not going to 0 fast enough, is the case. We need this p to be bigger than the harmonic. It needs to go to 0. The terms need to go to 0 faster than the terms of the harmonic series. Harmonic series is that borderline. Okay? All right, great. So a lot of times we can either just look at a series and say, oh, well, it fits. It fits one of these categories. Or we can leverage the knowledge that we've got based on these facts that to find out about other series. Okay. There's two ways that we can use these sorts of objects that we know what their behavior is based on certain criterion to leverage against others. So let's see, we've got the direct comparison. Direct comparison, I've got a series, A sub n. This thing, unknown. I don't know about it. It's a new thing. It's the one I'm actually testing, the series A sub n. Okay, and I've got a series, B sub n. Again, the terms A sub n and B sub n are all non-negative. They're positive terms. These tests are going to be for positive. And this thing I know, it's got a known behavior. Like maybe it's a harmonic and I say, okay, I know it diverges. Or maybe it's a P series with P equal to 3 and I go, okay, I know that converges. Okay? So our B sub n is known, and then our A sub n is what we're trying to test against. What our goal is with direct comparison is a term-wise comparison. Term-wise. I want to compare the actual terms of these sequences. I say, okay, if A sub n is less than or equal to B sub n, this is term-wise, literally the terms that I'm looking at. Not this worrying about adding them all up, just literally looking at the terms. If they're less, A sub n is less, and I know that the series B sub n converges, then I know for certain that the series A sub n converges. Then the series A sub n converges. Okay, in other words, I've got some sequence of terms. They've got to be going to 0, right? And I add them all up. This is my B sub n. I add them all up and I get a finite number. So I know that the series converges here. My A sub n, I know that term-wise, they're all less. They're all less than my B sub n's. Well, if adding up all the B sub n's went to a finite number, then adding up a whole bunch of numbers that are all less than that will also. Yeah? Okay. So in this case, our goal with direct comparison is to show less than a convergent series. If I can show that it's less term-wise than a convergent series, then I know that it converges. On the other hand, if A sub n is greater than or equal to B sub n, and the series B sub n diverges, well, let's see. I'm taking all these terms, I'm adding them all up, they blow up to infinity, or they do something weird, and now I'm adding a whole bunch of terms that are all bigger than that. Well, if B sub n blew up to infinity, then A sub n is definitely going to blow up to infinity, even faster. Okay? So then the series A sub n diverges. So in short there, we want to show less than a convergent series, then I can prove that it converges. or greater than a divergent series, in which case I can prove that it diverges. Now sometimes it won't work. This is sort of the easiest alternative test after the divergence test. Of course, that's going to be the first thing. Just take the limit. If it doesn't go to 0, then it diverges. If it does go to 0 and I need to do some more work, I'm going to look at it and say, well, does it look like something that I already know something about? Can I compare it to something that I already know something about, right? So let me show you a quick example. Let's say, series n equal 2, 1 over n minus 1. Okay, so here, this doesn't fit. I've got this function down in the denominator, so it's not like just a straight up geometric or a p-series or anything like that. So it doesn't really straight fit anything. I look at this and I go, really, the only difference here is this minus 1. If I ignore that business, this really looks like 1 over n. This looks like the harmonic series which diverges, okay? So this, I'm looking at this and it's like the series 1 over n, which diverges. The harmonic series diverges. We just proved that. Okay, so that puts me on the track of thinking it's likely, I think, that this one's going to diverge too. So that I'm trying to prove that it diverges, which means that I want to show that it's greater than, term-wise greater than. I want to show that 1 over n minus 1 is greater than or equal to 1 over n. Because if I can show that it's term-wise greater than a series that I know diverges, then I know that this thing is going to diverge. So let's see, n greater than or equal to n minus 1, so multiply that over, subtract, 0 is greater than or equal to negative 1. That is the truth. So again, I just start here. This is something we know patently true. Work my way back. This shows that it's term-wise greater than a divergent series. Term-wise greater than divergent. And so I can conclude, therefore, by direct comparison, that series n equals 2, 1 over n minus 1 diverges. It's greater than a divergent series term-wise. Now, again, we don't need to really worry about where this index started. I just shifted it over because I didn't want to start at 1 or 0 because I end up with a divide by 0. But again, removing, I don't know, I guess I haven't said that yet. Removing a finite number of terms will never change the behavior, the long-term behavior, whether it converges or diverges. It'll change the value to which it converges, if it does, but it won't change the fact that it does. Converging or diverging is a long-term behavior, right? Going off to infinity. So taking a few off the front, even any finite number off the front, isn't going to change it. Not in the long run. Going to infinity. Okay. Great. So that's a direct comparison. Again, we need to bring to a direct comparison some B sub n series that we already know something about. We know that it's a convergent P series, or it's a geometric series with r less than 1 or something like that. So that's one of the downfalls, I suppose, of both of these, actually, the direct comparison and then the limit comparison, is that we need to bring to it some other sequence or some other series that we know something about. So let's look at the limit comparison. Again, this is for non-negative sequences. And A sub n, our A sub n series, that's the series that we're testing. And B sub n is a series that we know something about. Okay, if that's the case, what we'll do is we'll look at the limit as n goes to infinity of the ratio between A sub n and B sub n. So we're going to look at the ratio of A sub n and B sub n. B sub n is the one that we know something about. We're going to put that downstairs. Okay, and we'll take the limit of the ratio. If the limit as n goes to infinity of A sub n over B sub n is L greater than 0. It's some finite number that's not 0. If that's the case, then both the series B sub n and the series A sub n have the same behavior. Either they both converge or they both diverge. So what we're saying here is we're taking the limit of their ratio and it comes out finite. That means the rate at which the B sub n terms are going to 0 and the rate at which the A sub n terms are going to 0 is the same rate, right? They cancel each other out and come somewhere finite. But we already know that B sub n is going to 0 fast enough for the series to converge. So if A sub n is going to 0 at the same rate, then it must also converge. And likewise, if B sub n is blowing up to infinity and A sub n has the same exact behavior as that, well, then A sub n has to blow up too. So if that limit is some finite number, then the series A sub n and the series B sub n both converge or both diverge. They have the same behavior. All right, if the limit as n goes to infinity of A sub n over B sub n is 0, now we got to watch this. It is 0 and B sub n converges. So, and the series B sub n converges. Then the series A sub n converges. You got to be careful with this one. If that limit is 0 and B sub n diverges, I get no information. It's inconclusive. I have no idea. Okay? But if this limit is 0 and B sub n converges, then A sub n has to converge. So think about this. We already know that these terms are going to 0 fast enough to converge. Now, when we look at A sub n in the long run, the comparison is 0. That means A sub n has to be going to 0 faster than B sub n is. But B sub n was already going to 0 fast enough to converge, which means that the series A sub n is going faster, and so therefore must also converge. On the flip side of that, if your limit as n goes to infinity of A sub n over B sub n is infinity, okay, so it's blowing up, and your B sub n diverges, well, let's think about it. We're comparing their growth rates. Now, B sub n, we already know, is not going to 0 fast enough. Okay, so the series B sub n we know diverges, but the ratio of these two is infinity. So A sub n has to be going to 0 slower than B sub n does, or maybe not going to 0 at all. Okay, so the thing diverges. Then series A sub n diverges. Again, it's important to note that if the limit is infinity and B sub n converges, I get nothing. It's inconclusive again. So this is the limit comparison test. Again, the failure with this, or not really a failure, but the deal with it is that we have to bring this B sub n series to the table that we already know something about. Okay. So let's try, I don't know, let's look at the series n equal 1 square root n over n squared plus 1. Okay, so the first thing I'm going to look at, if you hand me this problem out of the blue, first thing I'm going to do is take the limit. Just take the limit of the terms, right? The limit as n goes to infinity of root n over n squared plus 1. Well, clearly the degree is bigger in the denominator than it is in the numerator, so that limit is 0. Okay, so it is going to 0. I don't know whether it's going to 0 fast enough. I didn't get it that it diverges, you know, right off the bat. Okay, still have more work to do. But that's going to be the first thing I'm going to try. If I got something other than 0 there, well, then we were done. It diverged. Okay, I look at this and I go, well, it's not a geometric series. It's not a p-series. It's not anything, you know, that I can just fit to my form over here. So I'm just going to look and say, this is n to the 1/2. I'm concerned about the degrees, right, in the long run. So that's n to the 1/2 and n squared. 1/2 minus 2. This is what, n to the negative 3/2. 1 over n to the 3/2. So I'm saying, I think this thing is similar in behavior to 1 over n to the 3/2. Now, is 1 over n to the 3/2 something that I know about? Well, let's see. It's the n that's changing. This power is fixed. So this is a p-series. I say, well, 3/2 is bigger than 1, so this thing converges. This is a convergent p-series. Right? Okay. So that's what I'm going to use as my test against. This is the one I know something about. The series 1 over 3 n to the 3/2. So let's see. I have the limit as n goes to infinity of n to the 1/2 over n squared minus 1. Was it n squared minus? Plus. Okay, there's my a sub n. That's the series that I don't know anything about. Over 1 over n to the 3/2, which I know is a convergent p-series. All right, divide by the fraction is the same as multiply by the reciprocal, so I have limit as n goes to infinity of n to the 1/2 times n to the 3/2 over n squared plus 1. Well, that's 4/2, which is n squared. N squared over n squared plus 1. Limit as n goes to infinity. Well, this goes to infinity at the same rate as this goes to 0. So they cancel each other out. It's just the ratio of the leading coefficients. It goes to 1. That's someplace finite, greater than 0. Which is, this is some L that's bigger than 0. That means that the two series have the same behavior. Well, I already knew that this is a convergence p-series. So, therefore, by limit comparison, this original series, the series root n over n squared plus 1, well, it has the same behavior as a convergent p-series, so it converges. Okay. So this is how we use the limit comparison test. Again, we need to bring to the problem that b sub n that we know something about. Noise. Okay, so those are comparisons. We use our geometric and P series, things that we know about that very often, to leverage knowledge about new series just by comparing like that. Okay, alternating series. Alternating series are series that contain -1 to the n, a sub n, or series -1 to the n plus 1, a sub n. In other words, they alternate, they flip-flop. It doesn't matter whether it starts negative and goes, plus, if it goes a sub n minus, no. Let's say a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, so on, plus. Or if it goes negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 and so minus and so on, right? It doesn't matter. What matters is that they're flip-flopping back and forth. They're alternating signs. Alternating series are really nice in that it's enough for the terms to be getting less and less to 0. All right? So that's all we need to show for alternating series, is that the absolute value, the limit as n goes to infinity of the absolute value, we can drop off the negative, so we just take a sub n. Well, I'll leave it, okay. It's the absolute value. Fine. Without worrying about the flippy floppy, if this goes to 0 and a sub n plus 1 is less than or equal to a sub n, in other words, the terms are getting less and less and less going to 0, that's enough on an alternating series to imply convergence. Then the alternating series converges. Okay, so this is pretty easy, or pretty intuitive. Think about it. Like, no matter where I start, if I'm here, and then I subtract something smaller, and I add something smaller, and subtract something smaller, and add something smaller, and subtract something smaller, and add something, right? It's going to converge to a value. So it's enough with an alternating series that those terms are getting less and less going to 0. Now let's look at an important example. How about the series -1 to the n 1 over, well, I could have put that upstairs. Let's go like that, over n. How about that guy? That's got a name. It's very, very important. It's very similar to something we've already looked at quite a bit. This is the alternating harmonic. It's identical in every way to the harmonic series. So we got 1 and 1/2, 1/3, 1/4, 1/5, and so on. But it's flippy-flopping every time. So we're adding, subtract, add, subtract, add, subtract, back and forth, back and forth. Now, clearly, 1 over n plus 1 is less than or equal to 1 over n. In other words, we already have that it's constantly, it's monotone, decreasing, in other words. And we know that the limit as n goes to infinity of 1 over n is 0. That's nice. So that's enough. We have them that they're getting smaller, going to 0. In the alternating case, that means it'll converge. So the alternating harmonic converges. The alternating harmonic converges. by the alternating series test. All I have to do is look at the absolute value of it, right? It's awesome. It's much nicer. We don't have to worry about how fast it's going to zero. Just the fact that it is going to zero is good enough. But that, again, leads us to the alternating harmonic, which is a very important example, and it does converge. That leads me to, since we were looking at the absolute value of a series, let's say a series converges absolutely. Absolutely. Series converges absolutely if the absolute value converges. Okay? Series converges absolutely if the absolute value converges. Now, converging absolutely, or absolute convergence, is a very powerful statement. It's a stronger statement than converging. In fact, that's a theorem. If a series converges absolutely, then it converges. In other words, converging absolutely implies that the series converges. So let me write that. If a series converges absolutely, is there an E in there? Maybe not. No, there's not. Anyway, okay, if a series converges absolutely, then it converges. Okay, so absolute convergence is a stronger statement than converging. It implies it. Converging does not imply absolute convergence. If it happens that if the series A sub n converges, but the absolute value diverges, we say the series converges conditionally. The series converges conditionally. Prime example is the alternating harmonic. The alternating harmonic series converges by the alternating series test. The absolute value, which is the regular harmonic series, diverges. We proved that earlier with the P series. Okay, so in this case, the alternating harmonic converges conditionally. It converges, but its absolute value does not. Okay. So the next couple tests that we're going to look at, the ratio and the root tests, they're actually tests for absolute convergence, which is really nice because it's going to immediately imply convergence, and we don't have to worry about all these flippy-flopping signs and stuff. We just take the absolute value and say, don't worry about it. Oh, and by the way, we get the geometric series converging on the other side. Remember, let me just note that. We had for our geometrics, A, R to the N, we had absolute value of R less than 1. And what we showed earlier, we proved it for the positive side, right? Between 0 and 1 and then greater than 1. Okay, but we get it for free on using the alternating series test on the negative side, right? That if this is a proper fraction on the negative side, I'm going to take its absolute value as long as that's a proper fraction, it's going to go to zero and decrease to zero. And so by the alternating series test, it'll converge. So we get the other side of this. That's why it's absolute value of R. I can get anything from -1 to 1. We get this other side for free from the alternating series test, basically. Not for free, but not much work. Okay. Good. So there we've got complete the picture on the geometric series. Talked about absolute convergence. It's more powerful than convergence is. We've seen an important counterexample, the alternating harmonic. Alternating harmonic does converge, but its absolute value does not. And what we have left then is our tests for absolute convergence, the ratio and the root test. Now I'm going to be a little hand wavy about the root test. It doesn't really get used all that often, to be honest, and it has the exact same behavior and criterion as the ratio test does. You use it for nth powers. I'll show you an example of it. I mean, we'll do it, but I'm not going to belabor the issue. It's more about the ratio test. And the ratio test is actually really, really important. We're going to use it. It's kind of our fallback tool. It's probably going to be the immediate one once the divergence test fails on me, that I get the limit is 0. If it's not immediately comparable to something that I know, like a geometric series or a p-series, then I'm going to fall back to ratio test. And the advantage of a ratio test is that we don't need to bring any other b sub n series that we know something about to it. We're only looking at the series that we've got itself, and we're comparing it to itself. Basically, we're comparing one term to the next. Okay, so we look at the ratio test. In the ratio test, I'm looking at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so I'm looking at two consecutive terms in the same sequence. So I don't need to bring any other b sub n here to compare it to. I'm comparing the next term to the previous term. If this is less than a 1, then the series a sub n, let's call this L. Or maybe that's bad news to decide to do that. Yeah, that's fine. Well, no, it could be infinity. Darn. Okay, well, we're looking at this limit. So if the limit as n goes to infinity of the absolute value of the ratio of those terms is less than 1, this implies that the series a sub n converges absolutely, which implies that it converges. Okay. So if that limit is if it's 0 or 3/4 or anything less than 1, then rock on, we're good to go. That thing converges. And I think I can go back to yellow. I have another yellow piece here. I have a blue piece. Try blue. Okay, if this limit is greater than 1, if the limit as n goes to infinity of a sub n plus 1 or a sub n is greater than 1, or if it's infinity, so which would be greater than 1, then the series a sub n diverges. That's another nice advantage of the ratio test. Not only do we not need to bring another series to the table, we're just comparing the series to itself, but it's also a powerful absolute convergence test, and it has a criterion for divergence. So we get this really nice split split, that we can show it either way, except for the one case where if the limit as n goes to infinity of that ratio a sub n plus 1 over a sub n is actually equal to 1. If it's equal to 1, I don't know. It's inconclusive. Inconclusive. I'm going to have to do something else. Try some other different test, maybe integral test or something else. Okay? But it's rare. It happens, but it's rare that that limit actually ends up being equal to 1. Usually, most of the time, and especially when we're looking at our polynomials, our infinitely long polynomials that represent transcendental functions, we'll be able to take the definition of that series, just take its limit, comparing it to itself, bound it by 1, and say, okay, if this ratio is less than 1, then the thing's going to converge, and that's going to give us the interval on which that infinitely long polynomial is going to give us the correct answer. So this is actually a really very, very powerful tool, and the one that we'll use the most often. The root test has identical criterion to this, except we look at the limit as n goes to infinity of the nth root of the absolute value of a sub n. Okay? Absolutely everything else is identical. If it's less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, then it's inconclusive. Okay? This one, we use it when we have nth powers. So let me quickly just do a real quick example of that, and then we'll come back to the ratio test. Okay, let's say I have the series n equal 1, e to the 2n over n to the n. Okay, so I've got these nth powers. And I'm like, well, it would be really nice if I could just kill off some of the nth powers, right? And get rid of it. So I'll use the root test, and I'll look at the limit as n goes to infinity of the nth root of e to the 2n over n to the n. Well, by our power rules, this is e to the 2n over n to the n over n, limit as n goes to infinity, right? Because this is a rational power, 1 over n power, and then power of a quotient says that I can distribute it through. And it's just going to get rid of all this, right? All those nth powers are just gone. Actually, strictly speaking, I need the absolute value here, but okay. Limit as n goes to infinity of e squared over n. Well, this is just a constant. N goes to infinity. This thing goes to 0, which is less than 1. And I'm like, sweetness. Therefore, by the root test, it converges. So therefore, by the root test, the series e to the 2n over n to the n converges. Okay? So that's how we use that. It's not as often used as the ratio test, but it's helpful when we have these nth powers like that, because I can just take the nth root and get rid of it. This, in fact, implies absolute convergence, right? And so therefore, it implies convergence. Okay, so that was a quick example of the root test. Let's go back to the ratio test, which is the big gun, the cannon that we're going to use, the one that we use probably most frequently. So I'll do a few examples of that, and then that's the whole shebang. Let's look at the series n equals 0, 2 to the n over n factorial. Okay? Now, n factorial grows way bigger than 2 to the n. Right? Think about it. 2 to the n for any given n is going to be 2 times 2 times 2 times 2 n times. Right? But n factorial is going to be 1 times 2 times 3 times 4 times all the way up to n. So after 2, all of these are going to be bigger. So factorial grows way faster. In fact, the factorial grows faster than any exponential function of any base. Right? We'll just have to move this line down, further down, but eventually the factorial is going to start outstripping our exponential function. So that the factorial grows really fast, and it grows so fast compared to 2 to the n that it's way faster than the harmonic. Those terms are going to 0 very fast, very quickly. So this thing should converge, just based on that. All right, just looking at the growth rates, comparing the growth rates of 2 to the n and n factorial. This thing is going to 0, the terms are going to 0 really, really quick, way quicker than the harmonic. But let's do it formally. So I'm looking at the limit as n goes to infinity of the absolute value. Now I need the n plus 1th term. So I'm going to plug in n plus 1 wherever n shows up. I've got 2 to the n plus 1 over n plus 1 factorial. That's a sub n plus 1, the n plus 1th term, over just the nth term, 2 to the n over n factorial. Okay, so here's my a sub n plus 1, here's my a sub n, and I'm comparing them to one another in the long run. All right, this will flip up and that'll go down, so I'll have limit as n goes to infinity of 2 to the n plus 1 times n factorial over 2 to the n, so when I'll go downstairs, right, times n plus 1 factorial. Absolute value. Darn, plowing through chalk. Let's see, I'm just going to switch colors mid. Anyway. Okay, so the 2 to the n's, those just become 1, and I've got a 2 upstairs. Now the n factorial over n plus 1 factorial, we got to think about that. The n factorial, that's 1 times 2 times 3 times times n minus 1 times n. That's n factorial. Downstairs, I have 1 times 2 times 3 times n times n plus 1. That was n plus 1 factorial. So all of this stuff, it all cancels. Well, it doesn't cancel, it becomes 1. And I'm left with just 1 over n plus 1. Well, this is just constant. This will grow to infinity, so this thing goes to 0, which is less than 1. Nice. Therefore, by the ratio test, well, the series converges absolutely, and so we can conclude that the series converges. The series n equals 0, 2 to the n over n factorial converges. Again, we knew that, or I could see that already from the fact that this n factorial is growing so fast, but we got it here formally. We took that limit, compared it to itself, got something less than 1, bam. We know it converges. It converges absolutely, and therefore converges. Let's try how about, oh, I should have started with this one, my bad. I meant to start with this one because it's slightly simpler, but same diff. N equal 1 over 8 to the n. 1 over 8 to the n. Now, just looking at this is a what? 1/8 to the n. This is a geometric series where r is less than 1. So this converges just by the fact that it's a convergent geometric series. But let's do it with the ratio test, see how that works. Again, I'm looking at the limit as n goes to infinity of the ratio of the terms. So limit as n goes to infinity, the absolute value. I need the n plus 1th term, so 1 over 8 to the n plus 1. And plug in n plus 1 for n. And then 1 over 8 to the n. Sweetie sweet. That one comes up. I've got limit as n goes to infinity of 8 to the n over 8 to the n plus 1. Well, 8 to the n over 8 to the n is just 1. So I have a 1 over 8. Noise. 1 over 8 is less than 1. That implies that the series converges by the ratio test. Therefore, by the ratio test, the series n equals 1 over 8 to the n converges. We knew that already because it was a convergent geometric series, but now we've proven it using the limit, or the ratio test. Let's try one more that's slightly more complicated, and then we'll call it good. Let's try series n equals 0, n squared, 2 to the n plus 1 over 3 to the n. N squared 2 to the n plus 1 over 3 to the n. All right. Again, this doesn't really fit. I mean, I could try to compare it to 2/3 to the n, but that's not really going to work. I've got extra stuff and things going on. So I'll just look at the limit as n goes to infinity, the absolute value. I've got n plus 1 squared, 2 to the, now this is n plus 1 plus 1. N plus 1 plus 1. So I've got n plus 2, that's n plus 1 plus 1, over 3 to the n plus 1. Maybe we'll just leave it. It's just weird for me. I don't feel comfortable, but it's going to come off anyway. So we'll see in a second. It's going to go away. All right, so that's my n plus 1th term. Now I just need my nth term. N squared 2 to the n plus 1 over 3 to the n. All right, so that's the limit that I'm looking at, comparing the two consecutive terms. This will flip up. So let's see, we've got limit as n goes to infinity. We have the n plus 1 squared, 2 to the n plus 1 plus 1. This 3 to the n comes upstairs. So 3 to the n over, we had, well, there's this n squared, 2 to the n plus 1, and this 3n plus 1, they end up downstairs. 3 to the n plus 1. All right. So let's see. The 2 to the n plus 1 and 2 to the n plus 1, those are just 1. So I have 2 to the first power that's left upstairs. I have n plus 1 squared from here. Now let's see. There's an n squared downstairs. I already took care of the 2 to the n plus 1. Now the 3 to the n over 3 to the n, that'll become 1, but I have a 3 to the first power left downstairs, so that'll give me a 3 here. Now I don't need to distribute this out. I don't care, right? All I care about is the degree. The degree of this is a square. That means they have this, this is going to infinity as the same rate as this is going to 0. They cancel each other out. It's just the ratio of the leading coefficients. So that limit is 2/3, which is less than 1, which implies that my original series converges absolutely, which implies that the series converges. All right, by the ratio test. That series converges absolutely, and so it converges. Nice. All right, so that's sequences in series. Again, it's important as you're going through all these, I know it ends up looking like a blur and all these different tests and stuff. Just remember that we're trying to represent transcendental functions as infinitely long polynomials and get a handle on that idea, which we'll see in the next unit. All right.